started, those printers started to go away, and he couldn't think of nothing anymore, and he wasn't working or doing anything. So he became kind of
Lost.
to what was next to be done, and the money was gone now. He didn't. See, that's another thing too. If you're in the business, like you say you are on the business side, right? You got some business. You're doing some business.
No, I'm doing my undergrad is environmental.
Oh, biomedical. Okay. But you want to know some business sense out of it, because the whole point is once you do, if you're going to start your own business, you need to know some business sense. Because if you don't, you're bound to fail. Because you don't have some sense of how to manage a business. You're all engineering. That's it, man. You're just, things work out right.
Hey Carl, how are you doing?
What's up, man? What's happening?
Nothing much. Hi.
Jason.
Leo.
Yeah, he's a, oh, you said you're in fine?
Oh, really?
You
Oh.
guys both, each other, you guys. Leo is, we mean, I've been with Leo. Leo, unfortunately, I have to leave tonight. So I was asking him I was going to ask you to download it for me, but Jason was able to get it for me.
Oh, okay, cool.
But,
you have to leave earlier?
Yeah, I got to leave. I had something I got to do, and I realized I had it. But Wednesday, you guys, the next Wednesday will be the last lecture.
That would be the final.
The final.
I think.
If I come by, can I get the last one from you? Because
Yeah.
I want to look at it, see what he's got. Because I don't know what tonight what he's going to say, because I got to leave.
Okay.
Okay. But you'll be here, obviously. You're going to be
Yeah,
here.
I have to be here.
Yeah.
I better be.
But yeah, you guys are both bios, yeah. So.
You just
But
started?
So he hasn't.
Oh, okay.
He hasn't been there, but he's been watching the lectures online
From home.
from home.
From home? So you're on then? Or are you an on-campus
I'm
student?
an on-campus student, but I still have access to the videos, so I watch the
Oh,
videos.
good.
Okay.
It's not easy for me to be here at night.
Yeah. Well, you know what? You did. The way things are in the environment, walking around. I know. I don't have a car.
483 with Professor Sartorius
You got a car.
on
It's cool.
Wednesday, July 30th,
You don't have a
2014.
car?
Yeah,
I
it's
don't.
tough.
I don't like really getting around without a car. If I have a car, I don't. Here, let me get you in a video. You know, I need to get your number, man, so I can call you, so we can, because this is the last run of the. Where's the professor this time?
What time is it?
It's 31.
Yeah, it's a little bit out. We already moved it, but if you got a number, I can call you. You gave me your email, right?
I did, yeah.
But you have a number, right?
I do, yeah.
Okay, well, that way I can get hold of you in the future. Hey, you want to?
Card?
You know, there's a 100 terabytes this guy's giving me for free.
What's that?
Claudia, here.
Claudia?
Claudia. Want it? Claudia? You got 100 terabytes if you go online. Hey, you can put your name right in this one. Yeah, Claudia is giving 100.
Oh yeah. I saw this. I saw it. Yeah.
Just of the heart.
I saw the email. I didn't open it.
Okay, produced it, did it.
Mhm.
And so, because I see people with stethoscopes, but unless it's an EKG reader, then you read the heart, but they don't have stethoscope sets.
Or the sound.
The sound. Yeah, you can actually get one.
Mm-hmm.
That was wild. And they actually put that together.
Yeah.
And it shows you all the code and everything about it.
So, okay, so this is homework 5. This is somebody else's homework 4. Let's see then. All right. Well, let me just say something that you probably not heard, given the age of everybody. What I have to say is, and you can remember this for the fall, welcome back, my friends, to the show that never ends. that actually was a song from the 60s. And you know what they say about the 60s? If you can remember the 60s, you weren't there.
Is your mic on?
Oh, no. No?
Never mind, no, it's on. Thank you.
Okay. Anyway, yes, well, tonight there are still a few things that I want to cover. We'll see how much I can. What's going to happen is that homework 5 is due tonight. Now, some students have asked for an extension, which is fine, but I can only extend it up till first thing Saturday, because I have to post the solution in preparation for the final. So, just to let you know. And also, your projects are due next week, so you can turn them in then if you want. But I've noticed a lot of students are working on them already, which is good. Now, I will have some review notes, just pretty much, you know, the final will be on stuff we've covered since the midterm. So, and then I will have a homework set, sample homework set, because there's still more problems that we haven't covered, because you know, there's more topics. So I will have a sample homework set that hopefully will help you all prepare for the final, which will be next week. So this is our last class. So I definitely want to finish the DFT tonight. We've talked about several things. If you really condense them, there's just 3 or 4 basic ideas, but the idea of the DFT, what it is. The other thing we've covered is a physical interpretation of the DFT. In other words, if you sample a signal at some sample frequency, then, and you do a DFT, then the one thing you want to ask is, when I look at the spectrum, and I look at a value, because the DFT values are discrete, if I look at a value, what frequency does that correspond to in the input spectrum? And how does it relate to the Fourier transform of the continuous signal? So we've been talking about that at some length, and in the last class. And then we talked a little bit about zero padding. And finally, last time, and I can just finish up with that, we talked about the, oh no, that's something else, the relationship of the DFT to the DTFT. Well, I should mention that. So what we found was that the DFT could be interpreted as related to the DTFT if you consider that it's a smooth version of the DTFT and it's discretely sampled in frequency, not from minus pi to pi, but from 0 to 2 pi. So we talked about how those points corresponded to actual frequencies, and then and how to handle negative frequencies, which aren't computed with the DFT. Only positive indices are computed. But we talked about the correspondence of those positive, or half the positive frequencies with the negative frequencies. So the pi over 2 to, or pi to, pi to 2 pi correspond to the negative frequencies minus pi to 0 because of the periodicity properties. And then finally, we talked about last time, which is kind of where I want to start, the DFT of sine waves. And we came up with this kind of neat little result, so I'll start right here, where we showed that the DFT of a sine wave, oh, I'm sorry, that's zero padded, sorry. Oh yeah, well, let me mention that while I'm at it. We talked about zero padding. And what we discovered was that when we take an input sequence of 10 samples and we add a bunch of zeros, you might think it doesn't make, you get the same result. Well, it turned out because of a peculiarity of the DFT, you actually get a little bit more information. Namely, you get more closely spaced frequencies. So as I said last time, zero padding, it doesn't really buy you any more resolution. It just lets you see the blurring. It doesn't improve this blurring. It's the same type of blurring you had when you didn't zero pad, but it will let you look at the details of that blurring and more closely spaced frequencies. Now, and so I said, so all zero padding does is let you see the blurring effect created by the window at more closely spaced DFT frequency. But I don't mean to say that that doesn't help. Actually, that can be a good thing, so I'll give you an example tonight of that. And then, finally, we talked about the DFT of sine waves. And we found this really interesting result, namely that if we have a sine wave and we compute the DFT, you can compute that analytically using this version of the geometric sum formula, or I came up with another way of calculating it using the convolution operation in the frequency domain. And when I did that, I found this handy-dandy little result that said that, it was right down here, that the DFT of a sine wave is equal to the DTFT of the window function centered at the sine wave frequency, but evaluated at the DFT frequencies, 2 pi k over n. So that is basically what the DFT of a sine wave looks like. So if we are talking about a rectangular, well, if we're talking about a normal DFT, rectangular windowing or no windowing, then the W is the sinc function, right? The W is the sinc function in the frequency domain. And so when you look at the DFT, and this is where we were last time, we had mentioned that I did a couple of different cases. One where the sine wave frequency was centered on one of the DFT locations. Now, as a result of the sinc function gives you its peak right there at that frequency, at equal omega naught is the peak, and since omega naught is one of the DFT frequencies, you will actually see that. But if you go off that peak to the next DFT frequency, because of the window function, you get 0, 0, 0. So if you took a DFT, if you computed a DFT of the sine wave, you can do it either just by MATLAB or by direct, or you can use this formula. Any way you want to do it, you're going to find that as long as the sine wave is centered in one of the DFT frequencies, some 2 pi k over n, then you get exactly a spike at the sine wave frequency and all zeros. So that's very nice. That's what you would, ideally, what you would expect for the TFT of a sine wave anyway, a delta spike right at the frequency you expect and then zeros. However, to show you the effect of the finite DFT, if I move the frequency of that sine wave over so that the sine wave is actually between two DFT frequencies, go back and look at this formula. Now you find that the peak of this sinc function occurs at omega equal to omega naught. But guess what? There is no DFT frequency in it. You're only going to get this function evaluated at the discrete discrete DFT frequencies. Well, there is no DFT frequency now at omega naught because it's right between two DFT frequencies. So we're going to get values on either side. And in this case, we have moved the sine wave so that it's right in between two DFT frequencies. So you can evaluate it using that formula. And if you did, you would find that, or you can do it using the geometric sum formula, but I like that formula. You would find that here would be the DFT frequency points, okay? So now you get what appears to be a whole bunch of sine waves, but it really isn't. And one way to interpret it, as we talked about last time, is thinking about all the power in the sine wave kind of leaking over into all these DFT cells because the sine wave isn't centered. So that's what you would see. And if you zero pad, which I had an example of that if you zero pad, you would just, it wouldn't really help. I mean, you know, in this example, I zero padded. I first took the case where the sine wave was centered in one of the DFT frequencies. And by the way, you can compute the DFT, the sine, again, I love this formula. So it's the same formula, the same W, it's just now at omega equal 2 pi k over P, where P is the zero padded version. But now you can see that if I zero pad out to 2n, so my data is from 0 to 10, so I go from 10 to 20 or whatever, 0 to 9 and then 10 to 19. So I just double the length by adding zeros at the end, and then I do a DFT. These are the values I get. So once again, you get in this case, the sine wave is centered precisely on a DFT frequency. So once again, you get the peak, and the peak happens to align with this DFT frequency. But now you're going to get a DFT frequency. You're going to evaluate a frequency over here at this point. You will find, because now you're doing it at omega sub k equal 2 pi k over 2n, see? So now you're going to get DFT frequencies that aren't at the nulls of the DTFT of the rectangular window function. So you're going to get values here which aren't zero. Here, see, so basically before, when the sine wave was centered, you got this frequency, that. Now you're getting the ones in between because you're computing more closely spaced frequencies, effectively by doing the zero padding, see? So that's why you get these guys, etc. And interestingly, now if I zero pad, but I move the sine wave over the frequency so it's right between the two DFT bins, see? So I'm doing these cases but with factor of 2 zero padding. So now I'm going to do this. So when I did this case and I zero padded by 2, then I did evaluate. See, this point was always there, but now I have frequencies that are lining up here, here, here. So I'm no longer getting just these frequencies. I'm getting the ones in between because I zero padded. And the same thing over here. When I moved it, I moved the sine wave right between two DFT points. Well, because I'm evaluating it now more closely spaced points, guess what? I'm actually going to see this point. I'm going to see this point. I'm going to see that point, etc. And so that will be the DFT of my sine wave when it's off-centered. In fact, if you compare these two, pretty much the same. This is the same as that, except it's been shifted over. So when you essentially have undersampled the DFT, now you get two distinctly looking much different DFTs, the way they look. And you might think, gee, what did I do? Well, you didn't do anything. You just sampled the DFT at kind of the minimal spacing so that you happen to get these points were very nice. Now when you zero pad by 2, you see more of the envelope, more of that, what I call that W. See, this is W of e to the j, omega minus omega naught, see? So when you in zero pad, you get to see more of that envelope. So that's what's going on. And now, in fact, these two look very similar, except they're shifted. So that's what happens when you zero pad. And this is a case, well, I'll pass on this. This is just if you have multiple sine waves, you can do this type of an example. So I said again, the zero padding does not reduce blurring. It only lets us see it more clearly. I'll have something to say in that in just a moment. And let's see. Okay, well, I mentioned this before. We don't have to, okay. So this was the rectangular window. Yes.
Is there like a limit for zero padding? Say you have a signal of 100 samples. Is there like a limit of zeros that you can add?
No, you can add as many as you want.
Or is there like a point where it doesn't help anymore?
Well, yeah, I guess that would depend on how, like if you had multiple sine waves, and like this case I was trying to show here, and they were very, if they were very closely, you know what, I have a better example. What if you have just one sine wave? Here, let's look at this example. This is an example from a project I did a couple years back, where what we were doing was I had a sine wave, and I had it moving around, and I wanted the student, and as part of this project, to tell me where the sine wave was located. And the way I told him to do it was compute a DFT of this sine wave, and look at where the peak occurs, and based on that peak, look at where the frequency corresponds to that, and that's their estimate of the sine wave. So I told him, do it with, first of all, I forgot how many points this was, but first do it without any windowing, and then do the same experiment again with a lot of zero padding. I didn't mean windowing, I mean without zero padding, and then do it again with a 4 times zero padded. So like if you had a DFT of 20 points, add 60 zeros to make it a DFT of 80. And here's what they found out. You know, what they found out was that if they didn't do any zero padding, you know, you get plots like this because your DFT frequencies are spaced apart very wide. So as it turned out, when they did the DFTs with the sine wave at this frequency, and they picked the peak value, you can see, well, sometimes the peak would be here. Sometimes it would be over here. But there is no DFT point right in between, see? So what that really means is that, and I think these are you had a frequency at, this is one of the DFT frequencies, correspond to 200 hertz, the other one corresponded to 100, but your sine wave was actually at 140 hertz. So your error, your RMS error was like on the order of 40 hertz, pretty wide, because sometimes you pick this to be the frequency. Actually, more often you pick this to be the frequency, but neither one were the correct frequencies. This is 200, that's 100. But now, if we zero pad, then it turns out that then the peaks start to show up more exactly because we have a lot more points. See, here we had sparsely spaced points. In here we had a lot more points, and so when we did, these curves are just different realizations, so you know, at different trials, but in all cases the error was so much lower because I had all these, I was computing the DFT at these points. So in all cases, yes, because it's a sine wave, I'm evaluating a sinc function. The length stayed the same. But because I've added a bunch of zeros, the peak of the sinc function I estimate much, much more exactly. So I guess to answer your question, if you added a lot more zeros, you might be able to even get better accuracy in the estimate of the sine waves. So when I say all that zero padding does is let you see the blurring more clearly, don't let that mean that it doesn't help. It can help a lot in frequency estimation. That's why people do zero padding as an example. So in any case, it's a good thing to do, and sometimes by adding a lot more zeros can help. So I'll scan that in so you have it, because I know that's not in your notes. So in any case, what I was trying to say here was, as we saw earlier, the effect of using only n samples is equivalent to the windowing operation. X of n is equal to x of n times w of n, where we've always assumed w of n was this, because that is the definition of the DFT. And when we did that, and I took the DTFT of W of the rectangular window, you get this sinc type shape, right? But what I'm saying here, you don't, when you do a DFT or when you do spectrum analysis, you don't have to restrict yourself to the rectangular window. There's a lot of other windows out there, and I will talk about one of those in just a few moments, but a lot of different types of windows. So that's what I wanted to say pretty much about the basics of the DFT. I did include in your notes an example where in this example it was an example meant to kind of mimic the radar type of example where in a radar scenario, or in this problem, what happens is you are attempting you have a couple of objects here. This one didn't show up too well, but one is a moving vehicle, could be your car, for example, and this is, think of this as a little radar gun or a sonar gun. And so the idea is you send out a pulse at a certain frequency, and you measure the frequency that comes back. If the frequency is shifted, that's due to the Doppler effect. And if you're on a line with this car, it's kind of moving at you or moving by you, you can kind of tell how fast this vehicle is going. Now, the only problem is, and it's more complicated this in the actual scenario, where you have the policeman standing with the gun and the thing. The only problem here is that, you know, that's not the only thing you're going to see. I mean, now the radar guns or the sonar guns actually have fairly narrow beams, so they can isolate just a few objects. But you might get a stationary object or some other object. Maybe the stationary object's closer. So the bottom line is, you send out a frequency here, you will get a different frequency if it scatters off a moving object. But off a stationary object, you're going to get the same frequency. So you could have the situation, if you're trying to do radar analysis in this two-object scenario here, where you have a return echo that's slightly Doppler shifted, but you have another echo, maybe it's much larger, which is not Doppler shifted. So your job is to figure out what is the Doppler shifted, so I can see if this frequency is pretty far off from the frequency I transmit. That suggests that you got a speeder coming here, see? So that's one way to use radar guns or sonar guns using this Doppler shift to measure the Doppler shift. Now the question is, how is that Doppler shift measured? Well, we can do it. We know how to do it by now using DFT, using DSP, using namely the DFT. So this is our scenario. This is our example. So I'm assuming that I am sending out this signal at some frequency. I'll call it F naught, and I'm listening. And as I listen, this is now. If there was nothing there, you wouldn't hear anything. So I mean, if there were no objects, then just radar would go out to infinity, and the aliens would see it. But in this scenario where there are objects, of course, which is where you use it, you're going to get echo coming back. You'll get a return. And in this scenario, we will assume that the echo, there's just two objects. In the actual situation, there are a lot more, but we'll assume two objects. And since I transmitted a sine wave, I'll get back a sine wave. And to make our life simple, I'm assuming complex sine waves, although of course you will have real. But so I'm assuming that the return signal will be some amplitude times the frequency I sent, plus, or actually a much smaller amplitude times a slightly different frequency, okay? And this I'm calling the secondary echo, and this is the secondary. And in this little case study, I will assume it's much lower amplitude, and this I will call the primary. Now, the primary is not much information. It just tells you there's something out there that's not moving that's reflecting some of this energy from your radar gun. But it's the secondary echo, of course, that you're interested in. And that's your case of interest. Now, what I will do, I'm going to fix some parameters in this example. I will assume that the primary is 30 dB larger than the secondary. So it's going to be a tough problem to try and detect the secondary because that has all the information. So I'm assuming, again, that the actually as an amplitude, the amplitude of the primary is about 30 times larger than the amplitude of the secondary, or in dB it's 30 dB larger. I will assume that we have a carrier frequency nominally of 100 megahertz. That's the F naught. We will vary it, though, in this case study. And again, delta F naught will represent the Doppler frequency. Now, what I'm going to assume is that that Doppler shifted, I call it F sub 1, we're going to fix it. We're going to fix it at a slight offset from 100 megahertz. We're going to fix it at a 1 kilohertz offset from 100 megahertz. So F1 will be a frequency 100 megahertz plus 1 kilohertz, or if you're into the floating point representation, it's 1.00001 times 10 to the 8th hertz. So it's very slightly offset. It's not much, but if we're clever, we should be able to detect it, even though the primary echo sitting at 100 megahertz or sitting at F0 is 30 dB larger. As you will see, we can detect that weak signal using tricks from DSP and the DFT. So we'll see how to do that. So I have a couple of cases. One case, we will let F0 be 100 megahertz. And so F1 is 100 megahertz plus 1 kilohertz. So F1 minus F0 for this first case is 1 kilohertz. Now, let's assume that we will sample, because initially we started out with this complex signal. It's a continuous time, but we're going to sample it so that we have no aliasing. We will sample it at exactly 2.5 times F0, which corresponds to 250 megahertz. Okay? And then what we're going to do is we're going to compute an endpoint DFT of that signal sampled at that rate. And so this is what that looks like. Okay? And that's our DFT. X of, I call it big X of EC of K. And it looks like this, where again T is 1 over Fs, and Fs is 250 megahertz, so T would be 4 nanoseconds. This is not a realistic example, but just for illustration. And I'm going to compute a lot of value. So the first question I ask is, what value of n, length of the DFT, would I need so that the primary and secondary echoes are separated by 5 DFT bins? Now remember, each DFT, the bins are equal to 2 pi k over n. Okay, those are the DFT frequencies. Or if you want, omega sub k over 2 pi, that is k over n. And we said that was equal to, I believe, well, I called it f sub k divided by f sub s. So there's 3 different ways of looking at the DFT frequencies. In radians, in a normalized frequency, okay, omega sub k over 2 pi, which is k over n, or in terms of actual frequencies, where fk is the DFT frequency in hertz. So this is radians. This unit here, I call that sample cycles per sample, but anyway, this is just dimensionless. And then, of course, dimensionless, and then, of course, in hertz. So we have 3 different ways of looking at it. What I'm asking is that I want a value of n to be large enough so that the frequency for the sine wave, let's call that omega naught, which is equal to 2 pi k naught over n, and omega 1 will be equal to 2 pi k naught plus 5 over n. Okay? I'm looking to pick a value of n such that this frequency falls on a DFT frequency, and that the separation is exactly 5 discrete DFT frequencies. So here is the answer to that. So what we're doing is we require, well, first of all, what is delta F? What is the frequency spacing between the DFT points? That is exactly F sub s over n. Okay, that is the frequency spacing between the DFT points, and that happens to be 2.5 times 10 to the 8th. That's my sample frequency divided by n. That's what I call my DFT resolution. So that's just F sub s over n. So if you looked at a one-cell difference, you would have, omega k plus 1 minus omega sub k divided by 2 pi would equal 1 over n. which corresponds to delta F over F sub S. Okay, that's just the spacing between DFT points in hertz. So that is my delta F. So what I want is, we require that 5 delta F, 5 of those spacings, we want that to be equal to F1 minus F naught. And we know that delta F, okay, so 5 times delta F is going to be F1 minus F naught. We've already set that equal to 1,000 hertz. So from that alone, we have an equation. We know what F sub S is. We know what, well, 1,000 hertz, so we can determine what N is. And what we will find is that N has to be huge. Namely, N has to be over 1,000,000 point DFT. Like I said, it's not a realistic example, but it serves to illustrate, okay? So if you chose, see, because if I ask you right here, before you do that, what is delta F? You don't know what delta F, because you don't know what N is here. But now we have an equation for N. We have an equation for N in terms of F sub S. So what we found was that, because we know the frequency spacing between the secondary and primary, namely 1,000 hertz. So we find that delta F is equal to 500 hertz, or I'm sorry, delta F is equal to 200 hertz, so 5 of those bins would be equal to the 1 kilohertz spacing. So we can say now that the secondary and primary is separated by 5 DFT frequencies, which implies that the frequency spacing between DFT points is 200 hertz, and it implies it's a 1.25 million point DFT. All right, so got that. Now, what does say you did all that, and now the question was you took this 1.25 million point DFT. What would it look like? Well, if you did that, you should find that the DFT would look kind of like this, okay? Because remember, the DFT of a sine wave is just the sinc function, and it's centered right at a DFT spin. We've done no zero padding, so it would be all these nulls. And the same for this DFT. The DFT of the little sine is also a sinc function, and it has nulls. So putting all that together, what you would see is nice 2 spikes. Spike here and a spike here. Now, if you looked at this in terms of dB, you would find this would be roughly, well, in amplitude, this would correspond to 30 dB. So it's pretty large, but you would clearly detect the sine wave, especially if there was very little noise. You would detect the sine wave, and when you detected that sine wave, you would note the difference in the frequency locations. You'd say, aha, that's a kilohertz of offset from here to here, because I can see the 2 peaks very clearly. So I would easily have a kilohertz of offset, and given a kilohertz, I could back out how fast this person was going, and you give him a ticket, or not, you know. In any case, so that's pretty much case 1. In fact, I even went a little bit further and said that if delta F is 200 hertz, then F naught is basically equal to K times delta F, and I found that K would be equal to, K, or I call that K naught. K naught would be, so you would see the sine wave for the K value of 500,000, and you would see the secondary sine wave at 500,005. So that's where your 2 sine waves would come. There would be just 2 distinct peaks. You could easily detect the one and detect, therefore, the frequency. So that's what the DFT would look like. And it all worked out because both frequencies, primary and the secondary, aligned with the DFT frequencies. That's why all that worked out for us. So this and this align with DFT frequencies. Namely, this is the DFT frequency at 500,000, and this is the one at 500,005. So that's what you would see. Now, yes?
Just say we don't know F1 and F naught, but we do want to determine N.
If you didn't know F naught and F1?
Yeah. So the principal components in your signal, you don't know.
Right. Well, in a case like that, if you knew, see, you would probably know a range. Well, first of all, in this case, you would know F naught because you know what frequency you transmitted. You know, you in this radar, you know the transmit frequency, so you would know F naught. The only thing is, you're right, you wouldn't know F1, but you would probably specify, well, look, I want to be able to detect velocities in this range, say, and that would translate into my delta F, my Doppler frequency offset from the primary. You would probably have a range of that. It might be, well, it probably wouldn't be 1 hertz, but it would probably be, you know, 1 kilohertz to 5 kilohertz. That say would cover all the range of velocities between 20 and 80 miles an hour. And given that, then given that spacing, you would know, okay, if my sample rate is such and such, I want my delta F, the spacing between DFT points, I want it to be a lot less than the range of frequencies I'm looking for. So you might have that F1 minus F naught would say anywhere between 30 hertz, well, say 300 hertz to 5 kilohertz or whatever, you know. So that would imply that your delta F, you would want it to be quite a bit less than 300 hertz. Maybe you'd want it to be on the order of 30 hertz. See, just to pick a number, or I'm sorry, 30 hertz. Say you would want delta F to be 30 hertz, then it would be a tenth of the minimum frequencies. And that in turn, you know the sample rate, that would give you an N. So you could do things like that. Now the situation's a little bit more involved than that because you have another variable, you have another degree of freedom we haven't talked about yet, but I'll come to that in a second. But here's something I want to point out. This gets into this other degree of freedom. Here's what I'm going to do. Again, this is contrived. You would always get your transmit frequency to be centered on the DFT frequency. But what if you have all the same parameters that we just had, 250 megahertz, 1.25 million points, secondary signal at 100 megahertz plus a kilohertz, but all you did was you moved, this is very interesting, you moved the primary signal from 100 megahertz to 100 megahertz plus 100 hertz. So what I did was I moved that frequency. I'm going to keep everything else the same, but I'm going to shift this big guy over, not one DFT. I'm going to shift him over exactly half of this DFT frequency. Now, I'm not going to change the sample rate. I'm not going to change the number of DFT points. So the spacing between DFT points is still going to be this 200 hertz. All I'm going to do is move this big sine wave over by 100 hertz right between these two. So let's see what happens. What happens is a complete disaster, of course. As you will see, what does the DFT look like? Now, well, you can kind of get a handle on that by, first of all, just look at the primary echo. It's the largest guy anyway. We ignore the little guy. He's not going to hurt us. What's the primary, the DFT of the primary signal going to look like? Well, it's a sine wave, and we know that it's going to be, regardless of what anything is, this is a general result. It's just the magnitude of the DTFT of the window function, which is the rectangular one. So it looks like this. So it's going to be the DTFT of that, centered at the sine wave frequency, which is offset now, evaluated at these DFT frequencies. Let's see what it looks like. Well, this is it. So our nice little DFT picture went from looking like this to now looking like this. And now it's pretty much, this is what the DFT of the primary signal would look like. And you can see now, when you computed the DFT, you would get these points, see? You're not going to see this anymore. This is not, because you don't have a DFT frequency here. Now, maybe if you zero pad it, okay, but we're not zero padding here. We have enough points already. So this is what we're going to see just from the primary echo. Okay. Now you ask the question, well, where is that secondary echo? Well, the secondary echo is just where it was before. It's right down here. Okay. Now, how far was it from the peak which actually occurs right here, the peak of the primary. Well, we said it was 30 dB down, right? The amplitude was 30 dB lower. But if you look at the side lobes of this window function, you see you get, this is the sinc function, you get its side lobes. So you get a DFT point here, and then you get one right at the middle of the first side lobe. And how far is this down? 13 dB. Still larger than 30, but it's okay because that's not where the secondary echo is. How about the next one? Well, you would find that it's 18 dB down. It's getting lower, but still quite a bit above the 30 dB. What about this guy? 20 dB. So by the time you get to the frequency of the secondary echo you're trying to detect, your leakage from the primary is only 23 dB down as compared to the secondary echo, which is 30 dB. So what's going to happen is these leakage from the primary signal are going to destroy detectability of that little secondary echo. So when you combine the signals together, this turns into hey, you're going to like this. I actually did a million-point DFT using MATLAB of this example. Well, no, I'm sorry. No, this is the first case. What is this? Yes. Okay. So let me show you what the DFTs actually look like. So I did actually DFT. This is case 1. This is what the DFT would actually look like in MATLAB, even using floating point. I mean, you say, well, that's not 0. No, but it's it's like 200 dB down. This is just this stuff here. If you actually, this is what you would see. This is just due to round-off noise, actually, just numerical noise. Okay, noise. I mean, even MATLAB, the precision isn't infinite. The numerical precision is fine. So you see all this stuff down here. But the peaks occur up around plus 100. This is minus 100, so don't worry about that. That's 200 dB down, so that's nothing. But what you would see if you actually did a 1.25 million point transform of case 1, you would see, actually you'd see something like this, and if you blew that up, which I did in this inset box, this is what you would see, just what I sketched before. You'd see again a spike here, and that would be a 30 dB differential. So that's good. That's what you would expect. And if I plot just the DFT of the, what is this? Oh, well, I guess if I superimpose the window function from the primary echo and computed the DFT, you would see here's the primary point, and then, as I said before, its points were 0, 0, 0, and right where the secondary echo, thank heavens, it is a 0. So it doesn't interfere with the secondary signal. So that's why you see the 2 spikes. Okay, that's fine. Now, let's go to the second case where I've just moved the primary signal over by 100 hertz. Now I'm going to take my million point plus transform of the 2 signals, and guess what I get? This is what I get. Now at first glance you say, well, that looks kind of like the first case. But it's much different. One difference right off the bat, look where this goes. It goes to 0 dB. Where did it go here? Minus 100 dB. Now, there's something different here happening. Something much different happening. So what is happening? What's going on? What is this? Well, I took this region and I blew it up. And what I found was this. And there's supposed to be, at this point, a secondary echo, which sticks up. You don't even see it, okay? You don't even see this secondary echo. Look, it's drowned out. It's drowned out by what I call the leakage from the primary signal, okay? And these points for the primary signal, that's what you see. That's what we just showed. That's with the window and all that in there. So here, all I did was move the primary over by 100 hertz. Everything's drowned out, okay? And if I blow that up even more and superimpose the DFT of the rectangular window, this is what you will see. So here is the rectangular window DFT, and when my sine wave is not centered at a DFT point, it's centered between two. These are the points you get. And what you will find is that, like I said, if you look down here, 1, 2, if there is no secondary echo, this is like 23 dB down. What you will find is that there's a slight increase in the peak at that point. That's due to the secondary echo, but you'd never be able to detect that if there's any noise. So you're pretty much out of luck in this case, okay? But you do have another degree of freedom. So here is the other degree of freedom. The window, you know. What happens if we use a triangular window? So I'm going to sample my echo at 250 megahertz, just like I did before. I'm going to take a million-point transform, just like I did before. But when I do my DFT, I'm going to multiply it by this window, see? This window is not the rectangular window. I'm going to let this window be what I call the triangular window. It looks like this. So I'm going to take my sample data over my 1.25 million points, and instead of just taking the DFT of that data, I'm going to taper it using this window. And let's see what I get. Oh, well, in any case, to a good well, first of all, what is the DTFT of this triangular window function? Well, it's no longer a sinc function. If you remember, this is why I'm saying it's going back and forth. It's tricky, but let's see if I hang on. Let's see. Let me try to pull that up so I can do side by side. I can't find it. But anyway, if you compare this, oh, wait a minute, I know I have it. Ah, there it is. There are two differences between this window function. Okay, there are two differences between this window, but the DTFT of the triangular window function and the DTFT of the rectangular. Here's the rectangular, and you see it's just a ratio of sines, okay, sine nx over sine x. This is a little bit different. This is the ratio of sine L times x over sine x squared. So that's one difference. You have an L, you have an N. What is the L? What is the N? Well, the L is stated here. L is approximately n over 2. In fact, it's equal to n over 2. That just happens to be the DTFT of a triangular window function. I showed what I derived that here in the notes, but that's not important right now. This is the window function, or the DTFT of the window function for a triangle. So it looks kind of like the rectangular, except it's squared, and instead of n, it's n over 2 in this argument. Now, what does that do? Well, it basically has the effects of two things. If you plot it out, which I did, it does two things for you. If you compare the DTFT of the triangular with the DTFT of the rectangular, you will notice two things. Number one thing you will notice is that this main lobe for the rectangular, it actually is bigger for the triangular. And that's a consequence of the n becomes L, equal n over 2, okay? Because now you have sine omega L, n over 2 divided by 2, again, actually n over 4, divided by sine omega over 2. And so the first null of this occurs when omega n over 4. See, there's an n over 2, and then everything's divided by 2. So it's never, when this is equal to pi, meaning that omega is equal to 4 pi over n. That's the first null. For this case, the first null occurred at 2 pi over n. So what has happened when you went to this triangular window function, which is, this is the bad part of it, is that the width of it expanded out by a factor of 2. So that's bad. But the good news, so there's bad and good news. The good news is, though, if you compare the first side lobe, look at that. That is already 30 dB down. That's the first side lobe. This first side lobe is only 13 dB down, 13 dB down. And the second side lobe is 40 dB down, 40 dB down. Now, where is our friend, our secondary echo? It's right at this frequency. So now the leakage from the primary into the secondary, and also you say, well, wait, is this the easy case or the hard case? Is this the easy case where omega naught was right on one of the DFT frequencies? No, this is the hard case. This is where omega naught was right between two DFT frequencies. Okay, it's centered right here. But if you look at its leakage back at the secondary echo, that's 40 dB down. And the secondary echo is only 30 dB down. So now we would have a good shot of being able to detect using that window. And in fact, here is my DFT, sorry, using, again, 1,000,000 points, so everything's the same. Like 25 times 10 to the 6. Fs equals 250 megahertz. And in this case, F1 is still 100 megahertz plus 1 kilohertz. F0 is centered. So this was this case where it was really bad for us with the rectangular window. Here is what the triangular window looks like. Now, one thing you will notice that I didn't point out before, now I can point it out, is that when you compare the DFTs, yes, if you compare, remember the DFT with when everything was centered up nicely with the rectangular window, it was down here around -100. When I move this over 100 hertz, you saw this, which was much, much higher. This is 0 compared to -100. So now it should become clearer, hopefully, as you look at this more and more. This large level is actually due to the side lobes of the rectangular window, the sine x over x. It's or sine nx over sine x. These are the side lobes. Look at that. These are the side lobes. When I use a window with much lower side lobes, down here, look, we're back to the -100 out in this region. What about in this region? Well, I blew that up for you. And what happens here is that if you look at the DFT close in, you will again see what we kind of saw before, except now you will see a much more distinct peak at the secondary echo. Okay? It's still, I mean, there's still a lot of leakage. But now you have a fighting chance of detecting this, in the presence of noise even, because it sticks out a little bit more. And here is a blow up of that again, where again I've superimposed the function, the DFT of the triangular window function. So you can see what happens is that right here you get a DFT frequency here and here. This is where if you just had the primary echo, this is what it would be, and it's like, I don't know, 40 dB down right about here. But when that gets added with the secondary echo, it pushes the DFT up a little bit, enough so that you would probably be able to say, hey, wait a minute, something is there, and maybe that's. And if you knew it was only the secondary echo and your primary, if you knew that was the only two things you would have in the field of view, then you'd say, aha, it's got to be the secondary. Of course, if your field of view is full of cars, then it becomes much harder, which is why some speeding tickets are not won. Or rather, I should say, the driver wins because he says, hey, there's no way. There's 100 cars. How does he know it's my car? See, but now, if you use a smart DFT, you might know. But anyway. So now the spectral leakage from the primary echo is 40 dB down at the secondary. Bottom line, we will be able to detect something. The secondary echo using a triangular windowed point. So the moral is windowing with the DFT is important. It's another dimension that you can add into your spectrum analysis, and the minimum resolution rule of thumb is not always accurate. In other words, the minimum rule of thumb says, well, as long as I have two sine waves separated by this delta f, I'll be able to detect them unambiguously. Well, of course, that's not true because of leakage. So anyway, the DFT is kind of interesting. Actually, I should say a much simpler solution to this problem is instead of doing this 1.25 million point DFT, you can do the O downsampling trick. And so what you would do is you could use bandpass sampling, but the other thing is you could first translate this frequency down to 0 by multiplying it by e to the minus 2 pi j f naught t, because you know what f naught is. Now you have everything within a couple of kilohertz. You can low pass filter it, then do an A to D at a much lower rate. You don't have to do a 250 megahertz, and then do a DFT of that. And so if you did that, you can work through the math. But the bottom line is that if you did that, so what I did was I moved everything down to, I moved everything down to 0 by multiplying by e to the minus 2 pi j 100 megahertz times t. So I picked this frequency to be 100 megahertz, okay? And I still had a offset in my primary echo, like I did before, and I still had my secondary echo 1 kilohertz away. But now, since I moved everything down, I low-pass filter it, and I can sample it at only 2.5 kilohertz, since my largest frequency separation at 0 frequency is now just this kilohertz. So I resample everything at 2.5 kilohertz, and I use not a 1,000,000 point transform, but I use a 1,000 point transform. And now this is my picture. Now you can clearly see everything. So part of the problem was the example I used, as I said, it wasn't practical. It was contrived because I was trying to illustrate how windowing can help. So in that case, it wasn't a fair example, but because this is how you would actually do that. So you're still going to get nailed out there. So you would actually translate this down and sample it at a lower frequency. But, so that's how you would actually implement this. But like I said, it does serve to illustrate the effects of windowing, etc. Moral of this story is always shift the frequency sampling rate as low as possible prior to a DFT analysis. Now, before we take our break, we have several more minutes. I want to discuss a different type of window. And in your notes, the DFT notes, part 7, that I uploaded a couple of weeks ago, you will find somewhere, I guess toward the end of the notes, you will find these notes that I have copied in. And I copied these because this is interesting. It's not actually covered in Mitra, but it is covered in Oppenheim and Schaefer. So I took Mr. Oppenheim and Schaefer and I copied the relevant pages in. Because he treats something called a Kaiser window. Now, if you look in the index of Mitra, you will find Kaiser windows, but you won't find them discussed in the context of spectrum analysis. You will find them discussed in the context of low-pass filter design, which I will talk about, too, after the break. The Kaiser window is just another type of window, okay? And instead of a sinc function, it's a different type of function. The Kaiser window is generated with the Bessel function. Not really important how it's generated, but it just, for right now, it is a different type of window function. And I call it W sub k of n, k for Kaiser. And so when you do a DFT, you multiply your data times that, and you do that sum. N equals 0 to n minus 1, minus 2 pi j k n over n. So it's kind of like when we did the triangular window, except that the Kaiser window is actually a whole family of windows, and it's parameterized. Yeah, it's WK of n. It's a function of the window length n, and it's also a function of a parameter I call beta, and we'll see what that beta parameter is. In the context of filter design. Oh yeah, I'm sorry. Well, if you, well, I've already defined what the window function is, so you can't. It's hard to read. But anyway, the Kaiser window looks like this. That's a Bessel function with argument beta times 1 minus. It's kind of a complicated thing. N minus alpha divided by alpha times square root of all that. It's kind of a mess, but in any case, you can see what I had there. But where alpha is equal to n over 2. So the basic thing is there's a couple of parameters. Well, one parameter is just n, so that's no surprise. Larger n is, the longer the window is. But there's this other shape factor called beta. Okay, now we don't have to understand, you know, how beta determines the spectral shape of it. We can just plot that. But in any case, it's a family of windows parameterized on beta. Different values of beta give you different window shapes. So what is done here that I've also copied in for you, scanned these into your notes on the DFT, I have shown you some examples right out of the Oppenheim and Schaefer of what this Kaiser window, again, this is WK of n, okay? And I will assume in this case that n is equal to 20. So we will keep n fixed, the length of the window, but we will vary this beta parameter, okay, that pops up. It's a shape parameter. When beta is equal to 0, guess what? You get the rectangular window. So that's nice. It includes the rectangular window. It's a special case. As beta becomes 3, as it becomes 6, 6, you see that the window shape starts to come down, right? And it goes to 0 at the end, kind of like what our friend, the triangular window, did. So you can get all different types of window shapes just by controlling beta. Now, these two plots, hopefully you can see, yeah, you can kind of see these. These two plots are in the frequency domain. Those are DFT of the windows. And this is kind of interesting. For this plot in here, I've kept the length of the transform equal to 20. So n is equal to 20 here. Oh, I'm sorry, 21. Oops, 21. Okay? So these are 21 point, yeah, it's 0 to 20. So these are 21. So in this set of plots, the length of the transform hasn't changed, but all I did was change beta, okay? And here's what you will notice, which is interesting, is that as beta goes from 0, in this case to 6, the window shapes change, not surprising. But in the first case, this is beta equals 0. You can see these side lobes are very high, okay? But the main lobe width from here to here is very narrow. Not surprising. This is the rectangular window, right? Because we just said beta equals 0 corresponds to the rectangular. However, two things happen as I increase beta. As I increase beta, the amplitude shape starts to taper off more and more to 0. In the frequency domain, the two things are the main lobe width starts to increase, it edges out, but the side lobes start to go down. So this is the beta equal 3, and if we go crazy and make beta equal 6, what happens is the main lobe width stretches all the way out to here, but the side lobes are so far down. This is beta equal 6. So you kind of have a trade-off going on here between side lobe and main lobe. Maybe you like the side lobe, but the main lobe is too wide. You know, you have say you have two frequencies, but the side lobe gets so fat that they're both in the main lobe. So that's an issue. But in the last plot, we do something a little bit different. For this plot, we take this final one, the beta equals 6, and we start to vary the number of points. See? So in this case, this case here, this is L equals 21. It should line up with the plot here because this was all done with L equal, or N equal 21, sorry. This big fat one is N equals only 11 points in our DFT, and this guy down in here is N equal 41 points, see? So the N equal 21, that's this guy, and that's what you saw before up here. But look what happens when you go to 41 points. See, when you window out to 41, now the main lobe comes in, kind of like it was here. And what about the side lobe levels? Guess what? They're all the same. Now you might say, no, they're not. This side lobe is a lot higher than this one. No, it's not. If I drew a straight line from here to here, no, straight line like this, they're the same. It's just that you see a lot more of the side lobes when you increase N. Like if you look at the second side lobe, it's the same. But you just see much fewer side lobes. The side lobe level only depends on that shape factor, but the width depends on N. So you might have a situation where you have two sine waves, and you don't want the sine waves to be in the main lobe, so you just increase N. So it turns out this is a very useful window for you to design when you're trying to do spectrum analysis. Not filter design, but spectrum analysis. So Kaiser himself came up with a set of handy-dandy formulas where he said, well, look, if we know what our maximum side lobe level we want is, and like I said here, it's the same, whatever N is. So let's say we want a side lobe level that's, I don't know, 50 dB down, okay? Well, that means that you're going to have to pick a beta so that that's true. And in this case, beta equals 6 works. But what if we wanted a side lobe that was 90 dB down? Well, we're going to need a different beta. What do we choose? Well, Kaiser came up with this empirical set of formulas. And what he said was, well, if your side lobe level, the maximum one, was only 13 dB down, and hello, that's a rectangular window, so you can just pick beta equals 0. But as you want larger and further down side lobes, then your beta changes. And he gave you a little formula, which you can plug in and figure out what the beta is. And then he did another thing. He said, okay, that's good. But now, what if I want a main lobe, this here to be pi over 100, or whatever you want it to be. This is plotted in terms of pi, in terms of omega. If I wanted that width to be pi over 1,000, then what value of L should what value of N should I use? There's the formula for that. And that value of N does depend on the side lobe level that you want, and as well as the desired main lobe width. So he's got a bunch of he's got two empirical formulas that tells you exactly how to design your Kaiser window for a given main lobe width and side lobe level. So you can put that together and use that for doing spectrum analysis. So let's take a look. So let's go back to our two sine wave examples. Let's revisit, that's how we'll end this. Let's go back to our two sine wave examples. Remember this by now. This is the thing that gives us fits with the rectangular window. Now we know why. So there it is again. This is the radar example. F0 is 100 megahertz plus 100 hertz, and F1 is 100 megahertz plus a kilohertz. We will assume this really bad sampling of 250 megahertz. And we don't know how many points yet. We'll come to that. But we want to be able to resolve these two sine waves, and now we're going to use a Kaiser window, okay? So, to achieve detection of both sine waves, we must meet two criteria. You can set up two criteria. You can extend this to more sine waves if you want. Criteria 1, main lobe width of the window centered at the primary echo, F0, must not encompass the secondary echo frequency. So basically, we want the main lobe width so that the secondary echo, we don't want the secondary echo to be so close that it's behind the main lobe width. So that's condition 1. So that's ultimately going to be a condition on the length of the transform. We want to pick the transform long enough that the secondary is not inside the main lobe of the primary. That's one. Two, the side lobe of the window centered at the primary echo, there's this guy, at frequency f0 must be much less than the amplitude difference between the primary and secondary echoes. So if we choose an RL to meet the first criteria, now we know that the secondary secondary echo is outside of the main lobe, but now we want to make sure it doesn't get messed up with leakage from the side lobe of the primary echo. So that's where the second condition comes in. The side lobe of the window centered at the primary echo, we want that to be much, much less than the amplitude difference. So let's continue on. And again, our ratio of primary to secondary, as we know, is 30 dB. So to meet and actually exceed these two criteria, here's what we're going to do. We will pick delta ML. We're going to pick that. We're going to pick that main lobe width so that it is exactly equal to the F1 minus F0. Now, before I go further, let me just define what that main lobe width is. Delta ML. That is the null to null, or the null to null width of this. Okay. So what we're going to do is we're going to make this. We're going to shrink this so that the null to null width is equal to the difference between the primary and the secondary echo. But to make sure the secondary is outside of the main lobe, the real question is, where is delta ML over 2? Well, that's going to be way down here, see? This width, delta ML, that's the null to null width, will be equal to the distance between the primary and the secondary. But the zero to null width, which you're really interested in, where does this thing go to 0? We're going to choose it so that it is about halfway between the primary and the secondary. So now the secondary echo is way outside. So in particular, we have delta ML to correspond to F1 minus F0. The zero to null width, delta ML over 2, is going to be equal to, well, F1 minus F0 is about a kilohertz, is 900 hertz. That corresponds to 450 hertz. So no problem with the main lobe. We're going to design this dang thing so that the secondary echo is way outside of the main lobe. Okay, so that's one. So that is our condition. Now that's going to ultimately lead to a condition for the length of the transform. But for right now, we will pick delta ML equal to this. Okay? And that's, of course, in radians, so we have to normalize the frequency by the sample frequency, multiply it by 2 pi. So that's what I did here. Because this sketch is plotted in terms of omega. Okay? Okay. And we will pick the side lobe. We will want the side lobe level of this window function so that it is, so that the side lobe level will be 10 dB below. So we know that the ratio of the amplitudes to the primary are 30 dB. We will pick the first side lobe level to be 40 dB down. Okay, so it's going to be 10 dB below the level of the secondary echo. So that's our picture. So we have something like this. If we were to plot the transform of the Kaiser window, I'll call that W sub k of e to the j omega versus omega, you would find that it would look like this. And here's F0, here's F1. You would find it would look like this. And that first null, or the first side lobe, would be way down. That would be like 40 dB. So we should be able to easily detect the secondary echo if we had a window function like that. But how do we design a window function like that? With Kaiser window, it's very simple. We can use the Kaiser heuristic empirical formula to immediately determine beta, and that's the formula. I blew it up. So that's the shape factor. And then this L gives you the number of points in the transform. And what you find is that you need a beta of 5.48. Okay, when you're just putting into these formulas, using these two criteria. That's all I'm doing. And if you wanted, you could make the delta even smaller. You'd have a larger L, and you could make A sub SL smaller. You'd need a larger L, or a larger number of points. But you could do it. You can do anything you want here. So I got a beta using these two criteria, 5.48, and I found, lo and behold, that I don't even need 1.25 million points, 1.12 million. So let's say I did that, and I designed, that was my window function. Let's see, I know I don't have it mentioned. So given these parameters, for the Kaiser window, we first generate the Kaiser window coefficients. And it literally is this simple. You set your n, I call it n before L, 1.12 e to the 6. You set your beta, and guess what? MATLAB automatically has a little MATLAB function built in that will compute the coefficients. It's called Kaiser, not surprising, and it's a function of two parameters. L, the length of the window you want, and beta, the shape factor. Okay? So I did that. I generated my W sub k, and then I took the DFT. So what I did was I said, you can do it like this. Let's see, how would you do it? FFT of x, that's my data array of endpoints, dot times WK. And you can restrict that to n, or you don't have to do that. Anyway, that's your DFT. That's how you do it in MATLAB. Okay? So it's very, very simple. MATLAB has already got all the hooks built in for you to do this. You do have to have the signal processing toolbox. So I did it, and look what happened. Without even messing around with different window files, I just nailed it. You can now see both frequencies are very clear, and the two frequency locations. That's the frequency of the I know you can't really see it, but that's the red dot is the frequency of the primary. Shows up right at the peak, and there's another red dot, it's hard to see, on the secondary, bingo, right on the peak. The two peaks are resolved, and it's great. You can easily, now you can look at this and see, there's got to be, you can blow that up and clearly see where the peak of the secondary is. So instead of trial and error, I'll try the rectangular window, I use 1,000,000 points. Here's how you can do it exactly using these empirical formulas derived by Kaiser. So anyway, very, very powerful tool, and after the break we will come back to this. Now there are two distinct peaks at the primary and secondary echo frequencies, and therefore the secondary echo is clearly detectable using a Kaiser window design. And like I said, you can make, you'll give different values for beta L, but you can even make it narrower, main lobe width, and even farther down to more clearly detect the two sine waves. So that's very nice with the Kaiser window. So the bottom line is using a Kaiser window and his design formulas, they really take the guesswork out of designing windows. So again, like I said, in practice, you would have, if you think about it, in practice, you would kind of know a range of delta F's, given the geometry and everything. You would know delta F, or a range of delta F's. Given that range, then you could pick your main lobe to be so that it's narrow enough that none of these would come into the main lobe, and you would pick the beta factor so that it was below a certain level, and you could use that. So that's how you would use it. And again, this is not in Mitra for some reason. He didn't use that part of the Kaiser window. So that concludes my DFT lecture. Now, I just for completeness, I will say a few words about the. I will say a few words. Jeez, what did I do? Oh, wow. Oh, what the hell happened? Something is going on. Anyway, I will say a few words about filter design. That's it. just said a few words. No, let me say a few more. Okay. There is a set of handout notes, and it should be clear to you. I don't have much time, so it doesn't surprise you. So there's a set of handout notes called Filter Design Part 9, I think, _9. And it had a lot of stuff in it. Since we only have a few more minutes, well, more than that, but anyway, you get the idea. I can't really say much about filter design. Don't know if it'll even be on the final, but I will put some sample problems on it so you get a little flavor of it. The stuff that I will cover is pretty straightforward on filter design, but in any case, I will just stick with FIR filter design and windowed FIR filter design. And you give me 3 minutes before the break, and then we'll take a break. So when you're designing a low-pass filter, there are typically 3 regions of interest. The first region is something called the pass band, okay? And that usually is the region that covers your signal of interest. Then there's the stop band, which usually there's noise in that or an interferer. And then finally there's a middle region called the transition band. And there is something called the pass band edge, omega sub p, the stop band edge, omega sub s, and then there is these amplitudes. Now, what the amplitudes are, you see them, they're called h sub p and h sub s. And what this is, I'm plotting the magnitude of h versus omega. And the h sub p, see, ideally in the pass band, you want the filter response to be constant. But of course, it won't be constant. In this case, I'm showing it decreasing a little bit. So the designer will come to you and say, look, in the pass band, I can only tolerate a 0.001 dB variation or an attenuation of 0.001 in the pass band, because I want it to be 1, but I can tolerate to be 0.99, say, okay? And that maximum attenuation in the pass band is called h sub b. Now it's called maximum attenuation because that's as low as as you allow your filter to be. Some people call it a design tolerance or error in the pass band. But you want this to be 1. So maybe you let it be 0.99 or whatever the criteria is. And the same thing in the stop band. You want that to be 0, but you will allow it to be something non-zero. I call that h sub s. That's called the minimum attenuation or error. Sometimes they call it the error, the max error in the stop band. So that's h sub s. And you will give the designer that. And your transition is you're giving that a frequency band for your filter to get from this in the stop band to this level in the pass band. And in this transition band, you don't really specify what sort of levels there are. It's just whatever it is to get from this level in the pass band to that low level in the stop band. And that width is called the transition width. Now, since the filter response typically isn't very good in this region, the ideal filter is great. It's 6 and 0. Or, I'm sorry, the ideal filter looks like it's this and then 0. Well, unfortunately, not an ideal world. So this is typically what you see with filter design, these 3 regions. So since you can't control the response of the filter, you want it to be an ideal low pass. You can't control its response in this transition region. You want to make the transition region as small as possible. So that's the basic setup. And as I said, there are a lot of notes that I had, but for this stuff, I'm really only going to cover just a little bit. And now, why don't we take our break? And I will see you in 15. I think we can finish it tonight. Here's your. This is almost very good. Huh? Do you want it? coming to the last lap. This is about it. Okay, so let me say a few words about filter design. I don't know, probably won't be anything on the final about this since we're just covering it now, but, well, I mean, it's possible, but, and like I said before with the midterm, I will let you know a couple of days before, after I made the exam up, what problem areas will be on the exam. Now, for the midterm, that didn't, I don't know if that really helped that much, because, I mean, we covered Z transforms and DFT, it didn't help, but it'll help here, because we've covered a lot of topics. So, I will, but I'll say more about that in a few moments. Let me try to get through this. So anyway, so if you ever talk to anybody who is designing a digital filter, you will hear them talk about passband, stop band, or passband edge, or width of the passband. They'll talk about transition bands and stop bands. That's pretty much what are the main parameters in the design, and also the amplitude levels, or the errors that can be tolerated in both the pass and stop bands. So that's pretty much it. And not surprisingly, the tighter these errors, like if you demanded that h sub b no larger, or no smaller, I should say, sorry, than 0.9999, it's going to make the design more complicated. The same thing in the stop band. If you say, no, my stop band has to be 10 to the minus 20, it's going to make the design very difficult and a lot more complex. So anyway, these are the parameters that typically pop up. And as I was saying, in FIR, so all I'm going to talk about is FIR filter design, and in particular, I will just talk about techniques. Well, no, I shouldn't say that. All I will talk about is FIR filter design, and I will start with, I should say that, the window design technique. Aha. The window design technique. Now, the window design technique is sort of analogous to what we were just talking about with the window DFT. Basically, this is ideally what you would like to have, okay? That's your ideal low-pass filter. And by the way, what is the impulse response of this? That's something we covered practically the first or second class, and it is, if this is in the frequency mean, if that's the window shape, then the impulse response is the sinc function, sine omega x over pi x, not sine omega x over sine omega. This is sine omega, well, anyway, you get the idea. This is a true sinc function. And as we pointed out before, it's not implementable because it's non-causal and it's infinitely long and it falls off very, very slowly. So we can't really design, obviously we can't design the FR filter to meet our design criteria with an ideal low-pass filter. But I tell you what we can do. We can design an FIR filter which will be a windowed version. So in other words, if this is my ideal impulse response, we can't implement that, but we could implement HD of n. W of n, we could do that. Where W of n is 0 outside of 0 to n minus 1. We could certainly do this. So this opens up the whole idea of applying windowing techniques like we did in spectrum analysis just a few moments ago to filter design using FIR filters. Okay, so, but before we go to that, let's a couple of comments, observations. So how would we design this or approximate this ideal low pass? Well, one idea is we just truncate it, okay? That's kind of a window, a rectangular window. So we just say our h of n is h sub d of n for 0 to n minus 1, and then 0 outside of that. So basically what that means is that instead of taking all of this, there's all these other points, obviously, you just cut it off from here to here. Truncate. Set everything else to 0. So basically it looks like this. That's one way, not a great way, because you miss the entire main center region of this ideal impulse response. So a slightly better way than truncation is, well, you're still going to do truncation, but before you do truncation, you delay it, okay? You move it over. And say if you want to design an FI or low-pass filter of length n, then you would move it over, you would center it around n naught, where n naught is roughly half of n over 2, or n minus 1 over 2, okay? So that would be a better way. That way you get the full center portion of this ideal filter plus some of its, well, what we would call side lobes, I guess. So that's good. So that is, so that's the idea. You basically, your FIR filter will just be h sub d of n minus n naught for n between 0 and n minus 1 and 0 outside of that. Now, that will introduce a delay, but we will assume the delay is fine, that we can tolerate a delay in the filter. So that's another way. That's a little bit better approximation than the first way, but neither one of these techniques are very good, okay? A much more general way of doing this with Windows is with this. A more general way for FI or window design is we take the h sub d and of n and we multiply it by window. Actually, what we would really do is we would take h sub d of n minus L over 2, or n over 2, times W of n. That's really what you would do. That turns out to be a much better approximation to the ideal low-pass filter. So again, h of n is h sub d of n minus n naught times W of n, where W of n is the finite window function. And in the frequency domain, we already know from all of our work from properties that, namely, if we want to compute the DFT or the DTFT of the impulse response of the filter, including the window, it would product in the time domain, convolution in the frequency domain. So if you look at this low pass, and I used to have a picture, I can't remember what that is. But anyway, basically, so again, here's the steps. You start out with your truncated version of the ideal sinc function, impulse response for the ideal low-pass filter. You truncate it. Actually, you multiply it by a window, which truncates it from 0 to n minus 1. Here's my fictitious window shape. And in the frequency domain, what that means is you take your ideal response, which is 1 and goes to 0, and you convolve that with the DFT of the window function, which we just saw. And what that does is, kind of like what it did with sine waves, it basically smears this region out. It blurs this sharp region out. And because of the side lobes, so you can see, here, once again, here's what that would look like. Let me draw. You would have your sinc function, okay? And you would have that, and then you're going to move that relative to your ideal, which is the rectangular, multiply, integrate, move it over a little more, multiply, integrate. What's going to happen is, as long as your window is fully contained in the width, this omega sub c, you're going to get, a fairly good value, but it's going to start getting smaller out here as the window moves past this edge. And once the window is over here, you get 0? No. You're going to get the effects of the side lobes, and they're going to ripple for that particular window. So this is more or less the type of shape you would actually see in practice in using this design technique. So here would be your you could think of this as your pass band. Here's your transition band, and here would be the stop band using this window design technique. Now in a moment, we will make that a little bit more, right now it's kind of loosey. It's kind of rough because well, wait, what do I pick for my stop band? What do I pick for my pass band edge? What do I pick for my errors? I don't quite know how to do that related. We'll show you how to do that in a second. But that is the low-pass filter design using a windowed ideal delayed impulse response. And a couple of notes on this. Delta omega is the transition width. And that kind of heuristic, now this isn't exact, we'll make it more exact in a few moments, but the transition width sort of depends on the main lobe width of your window that you're windowing this with. If you had a very tiny main lobe width, then your transition width would be very, very, very small, because it wouldn't take you much to get so once you get the main lobe width close to the edge of this, it doesn't take much for it to go outside, which is kind of where your transition band is. So the narrower the main lobe width, the narrower this region here, from large to small. Okay. Stop band attenuation. Well, the stop band attenuation, this stuff out here, it's going to kind of depend on the side lobe levels of this window. Again, this is heuristic, but just to kind of get some feeling. And another note is that we know from DFT that the max side lobe level depends on the window shape, like we learned with the Kaiser window. Vice versa, delta omega, we could make the Kaiser window main lobe width small, but that depends on n. So heuristically speaking, and we'll make this exact in a second, what this is saying is if I specify a very narrow transition region, that's going to translate into a large FIR filter. So what we'd really like to be able to say is, given that the designer specifies a delta omega, it specifies errors here in the pass and stop band, what kind of windows could you use? What sort of n values? What sort of lengths of windows do you need? Well, our friend Kaiser will come to the rescue on that in just a moment. So we choose window type based on stop band attenuation requirements. We choose the window length, or the length of our FIR filter, based on transition bandwidth requirements, as we'll see in a few moments. So you could do a trial and error. I mean, if somebody give you the specifications for your filter, you could pick a window and pick a window length and go through this loop where you actually compute the frequency response, compare it with your desired. Is it work? Done. If it doesn't work, keep going back and modifying the window. So that would be one way of doing it, which isn't a very nice way of doing it, because it takes an iterative method. But we'll have a better way to do it with our friend Kaiser. We're not going to cover that. Frequency sample. As I said, we don't have a lot of time, so yeah, we're not going to cover it. So there's a section called frequency sampling, and you avoid that. Like the plague, we're not going to cover that. Okay, but, of course, it was typed neatly. Here's what we're dealing with. Here's my final lecture, and I got these handwritten notes, but that's all right. The FIR window design technique. Let me talk to you at least a little bit about Kaiser, the Kaiser design method. And this is in Mitra's book. Mitra does have a nice section on this. Let's see if I have that notice. Okay, this is hopefully, just a second, bear with me. Okay, well, it's one word choice. Yes, good. Well, took me a little bit of time. I'm glad I took that. Probably could have found that over. Anyway. So, okay, so this is actually, this is in chapter 10 of Mitra. This is Mitra section 10.2.5. Yeah, 10.2.5. So that's, like I said, I've jumped over quite a bit in the Mitra book. But in any case, this he does cover, and he does cover or talk about the Kaiser design technique. So here's what we're going to do. We're going to take and delay our ideal impulse response by an amount alpha, where alpha is approximately m over 2 or m minus 1 over 2 if m is odd. And so alpha is m over 2. And that's our h sub d, that's our desired impulse response. And then we're going to multiply it by our old friend, the Kaiser window. So that's going to be that. And I mentioned this a little bit before. The Kaiser window is this Bessel function window. And again, it depends on these two parameters, m, the length, and beta, the shape factor. So we know about those. M and beta can be adjusted to trade side lobe level with main lobe width. We saw that with the when we were talking about spectrum analysis. But now we're going to apply it to FI or window design. Okay. Going back to our original figure, we will define omega p to be the passband cutoff. And we will say that our error within the passband is between 1 plus or minus delta. Delta could be 0.01 or 0.001. And furthermore, and this is actually, as you'll see later, turn out to be a limitation of this window design technique, I will assume that in the stop band, the magnitude of h is less than or equal to delta. So, generally, if you want a very, very small stop band, then you will pick delta to be quite small, which in turn means you will have a small error in the passband, okay, because there's only one delta between the stop and the passband. Now, there are other window design techniques, or no, I'm sorry, not window design, but there are other FIR design techniques where you can specify two separate deltas. One error for the passband, one error for the stop band. But with this window design technique, there's only the one error. So the smaller you make the stop band, you're also going to make the error smaller here. Which sometimes it's not a great thing, because sometimes you would like a little sloppier in the passband to get the stop band attenuation. It really helps the design. It simplifies the design. Okay, so that's the idea. So here is our window design technique. Let me write that down. H sub d of n minus n over 2 times w sub k of n. Now the one thing is, you recall h sub d of n minus n over 2 is equal to sine pi times, I'm terrible with, what was that format? Sine times pi omegas, no, oops, is equal to sine omega sub, here it is, n minus n over 2 divided by sine of, divided by pi times n minus n over 2. Okay, so the first thing you will want to know is, what do I choose for omega sub c? See, well, if you look at the little plot, it's not a great one, but in any case, what I've shown is the, let's see, maybe I should use the original plot. Or maybe we should go home. Oh, no, I'll try to muddle my way through this. So basically what we're going to do with the window design, with the window design technique, what we're going to end up doing, you know that omega sub c, here's your pass band, here's your stop band edge. With the window design, we're going to pick omega sub c to be right in the middle of these two regions, okay, right between where it transitions down. Now, you say, well, no, but for the ideal, it ends at omega sub p. That's the ideal. This is an approximation using the window design technique. With the approximation, omega sub c is a parameter. And we will choose that parameter to fall right between the pass band and stop band edge. So that will set our omega sub c. So that will be omega sub p plus omega sub s over 2. So that fixes the only unknown parameter with this, with the ideal impulse response. That's the only unknown parameter. You know what big N is, and everything else is fixed. So, so that's that. What else? Let's see. Yeah, okay, I talked about that. Now, the neat thing about the Kaiser design method, which is the neat thing we saw when we applied it to spectrum analysis, is that Kaiser once again came up with a relative simple approximation of a formula that relates the tolerance, the error in the pass and stop band delta, and delta omega, which is the transition bandwidth. He came up with a formula which related those two to, guess what? The length of the filter of the window and the shape parameter for the Kaiser window. So he did it again, and his formula for the shape parameter, if you call A minus 20 log delta, so let's say as an example, delta were 10 to the minus 4, then A would be 80, see? That's the dB down where you want the stop band to be. In other words, the stop band can be no larger than 80 dB below the peak in the pass band, which is normally 0 dB. Okay, so the smaller you make delta, 10 to the minus 4, 10 to the minus 5, A would be 100 dB down, see? So you're going to specify that. Now again, you would like to specify an error tolerance in the pass and stop band. Unfortunately, you can't do it with this window design method. But, oh well, at least you have simple design formulas. So, so anyway, given that delta, that error tolerance, then he came up with a formula for the shape parameter. Now, if you look at this, it kind of, well, that looks like what we found for the, it kind of reminds you of the formula we had for the spectral estimation. But if you look carefully at this formula and the one we talked about for the Kaiser windows for spectral analysis, they are different. They're different formulas. But this is the formula that works for the window design. And so that gives you the shape parameter. All you need now to know is how large of an FIR filter do you need. He came up with a formula for that in terms of, no big surprise, delta omega, the transition bandwidth. So here you see that relationship. M is inversely proportional to, inversely proportional to delta omega. Tinier the main lobe width, the transition width rather, I should say, the larger the FIR filter length. So he's got a formula which relates, so all you have to do is tell him, look, I want to design an FIR filter, I want a very narrow transition width, and I want an error tolerance to be such and such. He can tell you very accurately how you would design it using the Kaiser window. And kind of the final, almost the final thing here is that I have this example, contrived, but kind of give you an idea. I have a signal, and I'm trying to sketch, this is almost a cartoon, it's laughable. But anyway, I have this signal where I have this is kind of, could be a voice signal, it looks like this, and then I have an interferer, a sine wave interferer, that's not drawn to scale. It's 40 dB larger than the peak spectral level of the signal itself, and the signal ends at 5 kilohertz, and the interference is at 10 kilohertz. So my question is, how would you design a filter? And to make life a little more interesting or difficult, as you want to look at it, I've added some noise. That's kind of broadband noise in between the interference and the signal. So, and I sampled this all at 25 kilohertz. So this very simple example, contrived as it is, kind of shows you how to play around with some of these parameters. So, I want the stop band attenuation to be 70 dB so that I want the stop band attenuation of this filter to be 70 dB, in which case the sine wave will be 30 dB below the signal after filtering. So here's 40, subtract 70, I get minus 30. So that's pretty good. That's a lot of stop band attenuation. Okay? And where do I set my passband cutoff? Well, let's initially set it right at 5 kilohertz. So whenever the signal ends, that's when my passband ends. Okay? So I will set that. Now, how about my stop band? Well, I could have my stop band all the way down here. That'll get rid of the interference. But the larger the stop band, the more this noise gets in. See? So anyway, I could have my stop band anywhere between my passband, 0.4 pi, and my interference signal, which translates into 0.8 pi. Now what I did, you notice this? I translated the frequencies in hertz back to the dimensionless frequencies in radians by that formula, 2 pi times f over fs, which we learned from sampling. Okay? So I would like to make this transition band as that's kind of the maximum transition band, but I would like to make it as small as possible to get rid of all that noise in between the interferer and the signal. So, what is beta? Well, it turns out that we don't have to worry about where we make the transition band width and all that stuff. We can already determine what the shape parameter is. And if you use the Kaiser handy-dandy formulas for FIR filter design, you will find the shape parameter is 6.76 with these specifications. And the length of the filter, I use this other handy-dandy formula with, remember, A is equal to 20 log the base 10 minus 20 log the base 10 at delta. So it will actually be 70 dB. Delta would be 10 to the minus 3.5, I guess. A little bit larger than 10 to the minus 4. So this is the value of m that I need. Now I didn't specify delta omega. I just wanted to show this relationship. But if I plug the other values in, 2.285, 70 minus 8, 62, I would find numerically the relationship between the transition band and m is this, 27 over m. So, if we didn't worry about that noise in between and we picked the maximum possible transition band to still get rid of the interference, we would find that transition bandwidth maximum value would be 0.8 pi minus 0.4 pi. Any larger and you'll start letting the interference in which case you would find that your m value, your length of your FIR filter, will only have to be 22. Pretty small. But if we picked m equal to 100, then we could get by with, or then that would give us a delta omega 0.27, which would be much, much less than the maximum we could tolerate. So you can play around, trade-off, and those are the formulas to do the trade-off between the, basically between the stop, or the transition band and the attenuation. So those are the types of, and these are the trades you can make with the FR filter length and the transition band. Okay. And then finally, what if we wanted a 100 hertz transition band? So that means even though this interferes out at 10 kilohertz away and the stop band's at 5 kilohertz, I'm going to make my transition band start at 5 kilohertz plus 100 hertz. Can I do that? You can always do it, but the question is, what sort of number of coefficients do you need? And it turned out if you plug it in, you would need 1,000 coefficients, 1,000 point FFT to do that. So it's a lot, but it could be done. Oh, do I have some good news for all of us? I'm just about done. Okay, except for one other thing I did want to point out. So that's the Kaiser window design. And then later on, Parks and McClellan came along. Now, this isn't like last year. This is back in the 70s. So this is all a long time ago. But Parks and McClellan came along and came up with an optimal way of designing FIR filters. And it's very complicated. It uses Fourier Fourier theory to do this, and approximation theory, and it's really very, very complicated to come up with the optimal filter design. MATLAB does it automatically. It has a routine that does it. I think MATLAB is something called Remez. MATLAB also has the Kaiser windows, you know. MATLAB has a routine called REMEZ, which is an optimal FIR design function that's already built in. But it's very, very complicated. But our friend Kaiser came along and said, well, I don't care about the filter, it's impulse response itself. I know that's complicated. But you know what I can do? He did it again. I can tell you how many coefficients you would need if you tell me what the passband and stopband tolerances are. And yes, they can be different. You don't have to make them the same. I have a formula which is perfectly general. You tell me what the pass, so maybe you want the stopband be 10 to the minus 7, but the passband error could be 0.01. You know, it's totally up to you. You can specify that, and you tell me the transition bandwidth, and I will come up and tell you how many coefficients you need with this optimal design technique. And you say, okay, but what is the filter response? Well, that takes a lot more work. But this at least gives you an idea of how complex of a filter you're dealing with. And again, delta 1 is the error in the passband, delta 2 is the error in the stop band, and there is the transition band between the stop band and passband edges. And here was an example I came up with, delta 1 of 0.1, or maybe I'm just showing that, delta 2 of 10 to the minus 5, and, let's see, no, is this, what is this? Okay, now here's an example, sorry. Suppose that delta 2 was 10 to the minus 3.5, so that minus 20 log of that was 70. And suppose that delta 1 was 10 to the minus 3.5. Well, it turns out this is just the example we looked at before. In this case, the optimum design formula would look like this, which I could write as this, 20 log to the base 10 of delta 1 minus 13, divided by 2.324 divided by delta omega. In the Kaiser window design formula, this was what we were calling A. In this case, delta 1 is delta 2. And you can compare this formula with the optimal. In fact, here I do it here. The optimal is A minus 8. This is A minus 13. So you're going to get a little bit smaller m. And in the optimal, you divide it by 2.285. Here you're dividing by 2.324 delta omega. So this is going to make, for the same criteria for the pass and stop band edges, you're going to end up with a slightly smaller number of coefficients if you use, in your FIR filter, if you use the optimal design technique. And I think I worked that out. Or did I? I didn't write it down here. But anyway, I computed M. You can do it using these formulas. But I got an M op. Well, I got this ratio, whatever that term. Well, I guess I left it as a function of delta omega. But with delta omega equals 2 pi times 100 hertz, remember that, over 25 kilohertz, I think that implied an M using the optimal design of about 950 or something like that versus 1,000 with the Kaiser window. So you really didn't save too much. But where you really save, as I point out in the second, you really save if your passband tolerance could be a little bit more giving, a little bit wider. So here was a case where, for instance, the stop band was still 10 to the minus 3.5, but the passband tolerance, I'd let that be a little larger, 0.05. So I can tolerate more error in my passband, but I got to keep my stop band the same. And when you do that, then you really gain with the optimal filter design. You can't do this with the Kaiser window design technique, but you can with the optimal design. Again, the formulas are complicated to derive the impulse response, but you can do it, and you will find that the number of coefficients are much, much less. Okay. That is actually, as I said, if you look at those notes on Part 9 on filter design, there's a lot because I talk about FIR and IIR. But I almost didn't have enough time for this, but I thought I'd give you a little flavor of filter design using just FIR techniques. So that's it. That's pretty much it. Of course, my notes I will scan on. Let me talk to you briefly about what will be on the midterm or final. And I think you will see where my little email that I sent out to everybody telling you specific topics to really hone in on for the final would be very useful because you will be amazed at how much we covered. Okay, so I am assuming it's going to be right here. We have plenty of room. It will be next Wednesday at 6:30. Either 3 or 4 problems. I haven't decided yet. I haven't even made up the exam. And the same thing is for the midterm, closed book notes and no crib sheets, because you will find that you will have everything you needed on the exam, like you did on the midterm. And again, bring your calculators just in case you may need them. I don't know. You didn't really need them for the midterm. And you will be responsible for all material I covered in class notes after the midterm. Now, one student said, "Hey, wait, on your syllabus, you had a lot of different topics. Will they be? No, they won't be on it because we didn't cover them, all of them. The final will only be on the parts of the notes that we covered and the book. So I have tried to summarize what these are. Okay, the first thing after the midterm was sampling, and this was covered in the notes sampling _5, and also in Mitra, section 4.2 in edition 3, 3.8 in edition 4. And the gist of this material, kind of condensing it into just a couple of equations, you should review the frequency version of the sampling theorem. You don't have to memorize it, obviously. I mean, if you needed to do this, the frequency mean sampling theorem on the exam, I would of course provide it for you, so you don't worry about that. But you should at least understand what the concept is. Understand the concept of aliasing, which occurs when there's overlap between the images. Remember all that? Yeah. Make sure you study that to get very comfortable with that. Okay, so Nyquist frequency, we mentioned that, which is half the sample frequency. You should, and of course the condition that you want the sample rate to be at least twice the bandwidth of the signal, or equivalently the max bandwidth, one-sided bandwidth, can be no more than half the sample frequency. So understand all that, those conditions. You should also understand the time domain version. You probably won't have a need to use it on the final, but I suggest just at least there's only a couple of pages of notes. I would at least briefly review those notes. And they only pertain to the no aliasing case, unlike the frequency domain, which is perfectly general. If there is no aliasing, then we can recover the signal from that formula, so you remember that. And then we moved on to the sampling part 2 notes. These were the notes we covered. We didn't cover all those. Here's what we covered. We talked about upsamplers and downsamplers. I'm sorry, no, this was actually in the part 1 notes. At the very end of the part 1 notes, _5 the date, at the very end we talked about digital resampling. That's right, so that isn't in part 2 yet. And, we talked about this digital resampler, for instance, where we do a rate expander. There might be a problem related to that on the final. I don't know yet. So there could be that. So like I said, a lot of topics we covered. We also mentioned the downsampling using the subsampler, and then you'd have to precede that with a filter. And even on this homework set, one of the possible problems was to derive this formula. Then we get to part 2 of the sampling notes. We talked about polyphase filters, and we talked about bandpass sampling. I guess in the part 1 notes, _5, I think we covered all of those. But in the part 2, what I'm calling _5-1, we didn't cover all of those notes. We didn't cover the A to D converters, for instance. But here's what we did cover. We did talk about the polyphase filters, and as part of that, we talked about the equivalence of these two structures. You saw that in the homework, in this last homework set. We talked about the polyphase decomposition, so I would review those notes, make sure you're familiar, or at least you're kind of comfortable with this concept. We talked about using this for decimation, and we came up with this. So, you know, obviously, what kind of problems could I have on this? Well, I couldn't have you deriving the structure, and I couldn't have you filtering a signal. I mean, that would require some MATLAB or something. But I might ask you a question about complexity of this. How many multiply? So go through my example that I give you in my notes on the underscore 5-1, the part 2 notes, where I actually went through an example of complexity and how it compares polyphase versus direct for a downsampler, okay? In any case, here it is, the polyphase downsampler, which, as it turns out, is equivalent to this. So that we covered, that you should be familiar with. We also talked briefly about a DFT filter bank, and you got a chance to try one out on your second project. So again, go through the math for this was pretty simple. I would definitely review that. And then we talked about bandpass sampling. So those were kind of the three basic topics, or really two, the polyphase and the bandpass sampling, and the polyphase channelized polyphase filter bank. So those are the three topics. Bandpass sampling, you should review those. That's 5 pages and those part 2 notes. And here are the relevant sections in Mitra. And, you know, basically we talked about how to recover a signal even if we aliased it, as long as we did the aliasing in a controlled way. So that's several topics in sampling. That's why I say when I look around on Monday to see an email that I post, kind of restricting your attention so you can really hone in on those specific parts, because there's a lot of topics. Sampling theorem, polyphase, downsamplers, upsamplers, filter banks, you get the idea. Bandpass sampling. And then we moved on, and that doesn't even talk about DFTs. We moved on to the DFT. We covered most of those notes. And, you know, we talked about the concepts, the definition. You need to understand the relationship between the DFT and the DTFT, okay? You don't have to memorize any formulas. Those will be given to you, but you should kind of review and make sure you understand how we said that the DFT was a blurred version because of the convolution of the frequency domain of the DTFT, and it's blurred by this transform of the window function. The Kaiser-Schaefer formula, we just talked about that tonight, but it's a simple formula, and that's another good one to kind of take a look at that section. There's only a couple of pages, but take a look. Yeah, just pages 68 through 70, and kind of tell you how you would design a Kaiser window for spectrum analysis applications. You should thoroughly, and I can't stress this strongly enough, you should thoroughly understand the basic relationships between the DFT frequency indices, the K, and the DTFT frequency, omega, so you should know omega is equal to 2 pi K over N, you know, that kind of stuff. And the corresponding analog frequencies. Remember that? F sub K equals K delta F, right? Where delta F was equal to F sub S over N. All that stuff. Make sure you know how to, simple formulas, make sure you understand are there. If you have any questions or you get any confusions, fire me off an email immediately. Anyway, those frequencies you should understand. And let's see, what else? And then finally, just a little bit we did on FIR filter design. It wasn't a lot, but it was a little bit. I doubt that I would have anything on the final on that, but you know, maybe there's a very simple problem I can have. In any event, and this is the most important part, I will post sample problems from past midterms. if you see a lot of sample on this homework 6, I'll call it. If you see it, you don't have to turn that in, just answers like for the midterm. But if you see a lot of problems on FR filter design, don't panic. That was from past finals where we had a lot more time. Like if you take this class in this fall or the spring, more than enough time to cover all this. It's just the summer compresses everything. But anyway, I will have some sample problems for you. And like I said, and I can't stress this enough, the big thing is to understand what the formulas mean. Don't memorize the formulas. Any formula you need will be provided. I will post solutions for homework 4 and 5. That'll be on the web, and the spatial homework set. That'll be on the web no later than 6. No later than Saturday. Sorry. You can see I'm ready for the lecture. Okay, well, that's it. If there aren't any questions. If you have any questions, please send me an email. So I will... have, and I'm not absolutely 100% saying this will happen, but chances are I should say. That's always good because it gives you a chance. Not wasting too much time. If you panic, you know, it's just guess. Okay, guys. It was a good class. I will